Okay, we're going to pick up from part 1, and we're going to kind of rearrange this. So part 2, we're going to construct an XOR gate. This is a very versatile logic gate, and we're going to use the AND and the OR and the inverter that we just learned in part 1. Okay. And then we'll go on to part 3 using the inverter, the triangle with a bubble, and create NAND, NOR, and XNOR. And then finally, if we get there, will be part 4. And this will be the half adder and the full adder. As you know, there's several full adders in the 7483, and that's just the lab that you just finished. So we're going from the actual logic diagram all the way inside that device to analyze the actual logic gates that make up that 4-bit adder. Okay? If you remember, we did the waveforms for the inverter over here. And these are the output waveforms for the AND gate. And then I'd like you to complete the OR gate waveform. So I did this already for you. You can see when that's a low and that's a high, it's still going to drop on a certain low there, and then it'll come back up at that edge and bring them up high again, and then there will be something happening here. So try to complete that. Again, this is the waveforms for the OR gate. Okay, we're constructing the XOR gates, as I mentioned, with AND, OR, and an inverter. So we have 2 inverters, 2 AND gates, and an OR gate. And here we are, we're actually describing the function here, the Boolean, or we'll learn Boolean shortly, but this would be, as I mentioned, this would be a sum of the products, SOPs. Here's a truth table for the XOR gate. Now this one gate, it needs all of these gates to design this guy. So it is kind of pretty versatile. But again, it takes up a lot of gates. Now you can also construct this with NAND gates and do some what we call universal gates. And we'll get there soon too. That just means that we'll be using other logic laws like De Morgan, and maybe we'll get into K-mapping soon. These are all reduction strategies to reduce the gate count. But go over this truth table here, and you can see that the only time that the XOR goes high is when any of the inputs here for A is 0 and 1, they're real 1. And opposite on that would be the A or the B being a 0. So only these combinations will make this particular logic gate go active, turn on, or produce a logic 1. Okay, that's what you want to remember. So the equation coming back up here for this whole circuit here is just A, B naught, or you can call it B bar, or A naught. And we need to correct this somehow. So we write this again. So we have A, B naught, A naught, B. So the logic equation for that will be A, B naught. Okay, so you can also write it with a bar if you and X being the output. Very versatile gate. This is where you'll see this actually in the adder circuits we did. Let's take a look at that real quick. And here we have a half adder. You can clearly see that there's an XOR gate, and that produces the sum output. And the carryout is an AND gate. So if you go through the table here, and you did this in your lab, well, actually, we'll go to the full ladder to illustrate that much better. Okay, but you see our very useful XOR gate. So let's go to the full ladder, because this is the, there's several of these in your 4-bit. But when you go to the sequence, your inputs, again, here are going to be A, B, and then your carry in and carry out and your sum. So I think you can probably go through this and verify, what you did in your lab one. I saw some of the results and they look pretty good. So let's look at the sum and the carry out for these last two. So we got A, 0, B, 1. Carry in is a 1. We have a carry out, 1. But sum, we have 0. Because we have a carry. Okay, 1, 1, 1 produces 1, 1, 1. Go through this logic, and again, you are not responsible for building this. This would be pretty, this might take a few hours, yeah? So again, my question is, how many full adders make a 7483? Okay, these are the, what we call the inverted. We're using the inverter to create, in this first, that's an AND gate, and then we're going to invert it. And this is going to give us our NAND gate. Okay? The representation or the logic function for that will be a bubble to get rid of this inverter. Although you could, but these NAND gates already have that built into that, and I'll show you the inner schematic on that in a moment. So what is the output for a NAND gate? Anytime there's a 0, it'll produce 1 or on. Okay. Now you look right alongside that, that's the representation of an AND gate. So you can see that these are inverted. So AND gate 0, 0, 0, 1. Okay. It's the same for the OR gate. This will turn into a NOR gate. Let me draw that again. That doesn't look too good. Okay, as we look at the NOR gate, anytime there's a 0 in the NOR gate, it'll produce a 1. Okay, but when you do a 0 and a 1, and then you have to bar that, so for example, 0 or 1 will produce a 1, so when you invert that, that becomes a 0. Okay, same with the other condition, A or 0, that'll produce a 0 because you're ORing it. That's 1 plus 0 equals 1, and you invert that. So that 1, when you invert the 1, that becomes a 0. And right next alongside that is the OR gate, and it's the inverted output of the NOR gate. Okay. Now you've already seen the XOR gate, and all we're going to do is add a what? This will be our last gate to go over. This is our exclusive NOR. And really it's an XOR gate, and then you invert it with the inverter, the 04, and then the logic symbol will be the XNOR. This is the actual symbol. This is using an XOR with an inverter. So here is the truth table. So you know this from your XOR. 0, 0 will produce a 0. 0, 1, that's when you want on a 1, and then 1, 0, that's also a 1. And if they're both 1, that's a 0. You can see that this is an inverse when we do the exclusive NOR. This is a 1, 0, 0, 1. So anytime the XNOR rather is both zeros, both inputs are zeros, or both inputs are 1, they will produce a 1. This is a very, very unique logic design implementation. So we want to definitely utilize that in some design coming up. Okay. So that's it for now, and then we're going to do part 4, which will be this will be the last part, but I guess we can probably skip this because you actually did this in lab 1, but now you know what's going on inside that 7483. So I think we could end this, we could all make this part of part 2, so we can start moving on to some other parts of the logic gates. Okay, and that'll be it. Thank you.